Okay, sorry for the delay. I think we're all set to go. So we have one of our own from CCOM, Kim Lowell, who has a background in forestry, data analytics, and forest biometrics. He'll be talking about analyzing LiDAR data using machine learning.
Thank you. That's very good in saying that my background is from forestry. I didn't hear any gasps like, how'd you get in here? Or who let you in, or anything like that. I do not have a marine or an aquatic background. I'm someone who is very interested in quantitative analysis, and typically it was done on terrestrial ecosystems. So being at CCOM for 6 months, a little bit of a change for me. Okay, so what I'm going to do, and I'm sorry, I'm going to have to look at the screen because I don't have the little thing telling me what's coming there, but what I'm doing is working on, as you saw with the title, improving mapping of shallow water by using LiDAR. So it's airborne LiDAR. Airborne LiDAR is quite useful, but of course nothing is perfect. So LiDAR point clouds are just very, very noisy. And if we get a little arrow, if you haven't seen them, this is LiDAR point cloud, and you can see it's quite fuzzy. It doesn't just have one single slice of things that we can just grab things out of. We've got all of these sort of other returns that have come back that are making it look a little bit fuzzy. Well, to do that, so processing that, in fact, to get the bathymetry out of it, to extract that and kind of wringing that out, it takes substantial time by human beings to do that. Now, of course, there's automated processing as that goes on. And in the course of extracting the bathymetry from the LiDAR, what NOAA uses is they use the cube algorithm that Brian Calder developed, that was developed here, which has since been enhanced to be CHIRT, which stands for Cube with Hierarchical Resolution Techniques. And so that's first slapped onto a LiDAR point cloud, and then afterwards it gets to a point where ultimately human beings have to sit down and start looking at the individual returns and the results of CHIRT. So the way CHIRT works is it establishes each of the blue points or green points that you see here are the equivalent of LiDAR pulse returns. These are actually for multi-beam, so it's sonar, it's not LiDAR, but the same principle. And CHIRT goes along and establishes a grid of points, which are the red points that you see up there. And those become what are called estimation nodes. So for each of those nodes, then, it takes a neighboring area and starts looking at those points and starts basically accumulating a frequency graph to say, these are the clusters that we're finding. And of course, in my example, they're beautifully separated. Of course, in real life, that's not the way it works. But the idea is the neighboring points are looked at for each estimation grid, and then a frequency distribution is looked at. And one of these, the term used that they are depth hypotheses. And so one of those is going to be assumed that is the correct one. And that's done that after a distribution like that is generated, certain things like a decision is made of which is correct if one has the largest number of points, or neighborhood node characteristics. So if you have one node next to this one that was very definitely that one, we will say, yes, we will assign that and say that's the correct hypothesis. Okay. What I'm doing is trying to improve those decision rules. And so what we're really trying to do is to see if we can estimate, rather than just take sort of an effective but brute force rule of what's the most common. What we're trying to do is say, well, if we can assign a probability of each of those points being bathymetry, then we can make a better informed decision. So for example, if I know that that particular pulse return has a probability of being bathymetry of 0.08, and it belongs to that hypothesis, that gives me an extra piece of information. And so if I have another point there and I say, well, that's a probability of being bathymetry of 0.01, it's also in that first hypothesis. There's another one, it's got a higher probability of being bathymetry, it's in a different hypothesis, et cetera, et cetera. Once I do that, if I can then look at the hypotheses that have been generated for this, and I can look at something like the mean probability of bathymetry, or there are other metrics that can be used, I can look at it and say, well, not only do I have these three hypotheses, but the highest average hypothesis, probability of being bathymetry, is that one, so I will assign it to that depth hypothesis. So what I'm doing is really trying to use machine learning to add that extra piece of information so that when the decision is made to choose one of these as the true depth, we have better information. So the approach that I'm using is to explore return metadata with machine learning. So the usual data that you get back from a LiDAR point cloud for each return is that you get the intensity of the return, which is then converted into a depth. So a pulse goes out, the intensity of the return comes back, it gets converted to a depth. Okay. Well, in addition to that, there's metadata that is provided with that. And when you send out a pulse, you can potentially get more than a single return, which you can see here. So some of what we get as the metadata is just the number of the return. So you've got the first return, the second, the third. You then get things like the first of many. You get whether it's or not it's a single return, and in this case, none of those three returns are single returns. Whether or not it's a last return, and of course that's the only one that's the last return. And then there are things like whether or not that pulse was collected by scanning in front of the airplane or in back of the airplane. So in this case, it's always a forward scan, so you get something like 111 for each of those returns. So that's the type of metadata that we're talking about. So that's useful for someone like myself who's a numbers geek. Okay, well, that's great, numbers to play with, fun things to do with that. But of course, we're only interested in that if that relates to the probability of those returns being bathymetry. Okay. So in doing that, there's a number of ways to analyze it. So the question to me really needs to be, whenever you're doing analysis, why are you doing what you're doing? Well, why machine learning, other than it's a miracle and it's going to solve the problems of third world hunger and human poverty and floods and everything, because it's just so miraculous. Machine learning has an advantage that when you look at all this metadata that you don't necessarily have intuitive interactions or forms of things, machine learning will find the interactions automatically. It also will address nonlinear relationships if those exist. And it will address, if you have the right data, whether or not these things are varying over time and space. So it is very black boxy, but in fact, you throw in some data and all of this stuff that needs to be handled is being handled. So what we're using, the LiDAR data, come from a Regal, VQ880, just the basic data stuff. It's a circular counterclockwise scan, so it's really the green here. There's also infrared LiDAR laser that's done, but we're only interested in the green. It's at a 20-degree angle. It flies at roughly 450 meters, speeds 200 kilometers per hour, give or take. Up there you see the frequency of the pulses. We're getting about 500,000 returns, 500,000 pulses every second. So, lots and lots of information coming back. The info that gets provided then is, as I said, the metadata, which is the pulse intensity, which I already talked about. But there's also something that comes back called the SVET data, which is the smooth best estimate of trajectory. And so what that is, it's the location of the plane every 200th of a second. So it shows you the trajectory of the plane, basically the flight path. Okay, so that's the LiDAR data that we've got. Now the study area is the data. Once the data are flown, they're then cut up into tiles. And the tiles are 500 meters by 500 meters along a north-south grid. This is shallow water stuff, so we're only dealing with stuff up to about 17 meters depth. We have 4 tiles. I'm using 4 tiles. They have 1 to 7 million returns. And because our video worked before, this is, I'll show you these. This is in order of increasing depth. So the first tile that I'm using is fairly close to the Key West airport. Some of it is actually above water. You can see that, and all of kind of the orange stuff that you're seeing is above water. The other stuff is in very shallow water. Next one is a little bit deeper. This is the best behaved one. It's a very smooth slope. It's not very deep. It's the easiest of all the tiles. It's the one you give to the kids because you know they won't break it. They can't hurt themselves, things like that. The next one is deeper, but it has the complication that those orange things are rivulets in there. So it's very uneven topography. And the blue, there's no bathymetry in there. And then this one is far and away the most torturous one. So I test everything I do on this one. The reason this is difficult is because only 4% of the returns that I've got are actually bathymetry. So I'm looking for 4,000 returns, bathymetric returns out of about 1 million pulses. And then up in the upper left, that little thing is a little mound that's about 1 meter tall. And so it makes for a very uneven surface, which is kind of difficult. So in doing that, these tile data sets, as I said, they're not flown in squares. They're flown, as you can imagine, with flight paths. So the plane goes over, turns around, comes down, turns around, and goes back. And once the data are collected, then you have these flight paths, and data from the appropriate flight paths are extracted to give you the nice square tile. And in doing that, when you look at that, a certain amount of the data that are inherent in this, they come from this flight path, they come from this flight path. Again, it's 20 degree scan angle. So it makes sense that you're getting sort of stuff that's not directly into the plane. Okay, so the types of metadata, I've already talked about some of the metadata, but the idea is we're going to extract a bunch of metadata, and then we're going to attach it. I'm going to attach it to each one of those pulses so that I can analyze it. And the type of metadata that I'm using, I've showed you the return metadata, but there's also flight path metadata that can be extracted. There's also what I call topographic metadata, and it's all kind of blurs together, but you'll get a feel for it. So the pulse specific stuff I've already talked about. It's that kind of thing, but there's other things that can be extracted. So for example, as the scan is done in a circular direction, potentially anything that's related to the reflectance of the pulse back to the plane might be of interest. And so one of the things that might be of interest is as the plane's flying along, if we know that the mirror scanned in that direction, well, maybe that affects the reflectance of the pulse, maybe not. But it's one of those things that whether or not we're scanning in front of the plane, the back of the plane, to the left, to the right, what the angle is, that's potentially of interest. Another thing is that the incidence angle, we know that the nominal incidence angle is 20 degrees because that's the way the instrument is built. But in fact, because of yaw, pitch, and roll, that incident angle can potentially be different. So you've got forward and backwards. So this happens to be a broom, a push broom scanner or a side sweep scanner, but the principle is the same, that if the plane is pitching or rolling or yawing, instead of the maximum being a 20-degree angle, the incidence angle with the ocean may be quite different, particularly since some of the data are sometimes collected when the plane's like that. All right, so that's kind of the pulse metadata, flight path metadata. I talked about the SBET data, the smooth best estimate of trajectory. That is the flight path, effectively. With that flight path, you also are provided with the standard deviation, the X, Y, and the Z position of that, which is a measure. It comes from a Coleman filter, we think. The manufacturer is pretty tight-lipped about where it comes from. And with that, though, we get a measure of the certainty of the position at any given time. So the certainty of the position might be useful to us because if the certainty of the position is changing a great deal, it suggests that the plane is being bounced around. And if the plane's being bounced around, it may be because the wind is high, which in turn may affect the surface characteristics of the ocean. So we may be getting some effect of reflectance because of the waves or whatever it happens to be. So that's one of the things that we can use for the flight pattern. The other one, I'll call it's a homemade, it's my stuff, of quantifying how much the plane is bouncing around. And where this comes from is that's very typically a LiDAR point cloud. So the gray is point cloud, that is the flight path, that's the SBET flight path. It's very, very nice and smooth. But the thing is, when you look at the edge of the LiDAR point cloud, that's not smooth at all. So even though we have the flight path, there's information there potentially that suggests that the flight path is not in fact very smooth. So maybe in those areas in particular, it was really gusty when that was, that information was collected. And again, maybe that impacts the yaw, pitch, and roll. Maybe that the incidence angle I can get, but maybe that impacts the characteristics of the ocean when the reflectance was done. So what we can do with that is that we can say, well, there's the SBET flight path. We've got the edge of the LiDAR point cloud. I can drop a line that says, well, when I started, this was the edge of it, and up there is the end of it. I can then extract the points that are the edge points, and from that, I can start taking the orthogonal deviation of the line to the edge points. And again, that gives me a measure at some point in time. If I have a big deviation in here, then something very different is going on than something over there, or with the LiDAR point cloud that I showed on the other direction. Okay? So this is another form of information, and then there are ways of quantifying the crenulation of the black points that you see, whether or not they cross the straight line, how often they cross the straight line, those sorts of things. Okay, so that's the flight path type of metadata. Topographic metadata, the seafloor characteristics matter. There was an article by Perry et al. From somewhere up in New Hampshire somewhere that said, titled, "The Seafloor, a Key Factor in LiDAR Bottom Detection," peripherally related to the types of things that I'm doing, I think. So with that, we're trying to extract topography. So what we're going to do is, with the data that we have NOAA's classification of whether or not something is bathymetry. So we can extract the bathymetry, and then we can create a DEM from that information. Problem with that is the points don't cover the entire area. So here is my my favorite tile, because it's my black beast, that the colored points are the actual bathymetric points. There's a couple right there that you can barely see, but the idea is that what we'll do is we'll interpolate those points within the convex hull. And the convex hull goes a little bit further than that, but it has to be cut down because otherwise the slope could go off a cliff. So bear with me with that. So we interpolate with that. Once we have an estimate of the elevation for everything within that convex hull, what we can then do is we can extrapolate beyond that. And the way I extrapolate beyond that, and there's no good way to do this, and this is one of those things that you say, well, that's absolutely absurd. It's like saying, what's going on the other side of this wall? That's exactly what it's like doing. You've got to do something, and if the topography is not useful in the predictions, well, that's fine. I haven't really lost anything. So what I do to do that extrapolation is I throw spokes out there, and what I'm trying to do is get an estimate of elevation there, and there, and there, and there, because once I can get an estimate of elevation outside of the entire tile, I can then go in, re-interpolate, and I can start filling that in. Okay. So to do that, for a typical one of those. I take that one, I extract the points that are at the very edge of it, which you'll see there. And once I get those, I regress those X and Y out to Z direction out here, assuming a linear relationship on those ends. I also double check to see if the root mean square error is too big for that particular regression. If it is, I don't use it because I don't actually need all those points. And then once I get that, I can go back in and I have points at the exterior. I can get the elevation from which I can extract the slope, the aspect, and then I can extract those for each of the pulses I have. And so now I have a complete data set where every pulse has all the information that I need. Okay. And then I can extract things like the orthogonality of the pulse. So for example, up here, you can see that if I have a pulse that comes in, it's perfectly orthogonal to the slope and also to the aspect that I have that's potentially different in reflectance characteristics than something where the slope is like that, or that, or that, or the reflectance is like that. So I can extract additional information from that for each pulse. So then it comes time to analyze the data. The way I'm analyzing the data, I'm using 3 different machine learning techniques. Artificial neural networks, because no machine learning presentation is complete without at least mentioning artificial neural networks. Extreme gradient boosting and regularized logistic regression. Neural networks, you've all seen a diagram like this. Okay, neural networks were in fact first formulated in 1943. Okay, so like a lot of machine learning stuff, the concepts of this stuff are quite old. They've been around for a long, long time. The idea is you put your data in, you structure your network somehow, and you get some output out. Okay, very, very black boxy. Handles interactions, linear relationships automatically. You don't have to specify those. Turns out that if you throw in too many variables, you're getting too much noise, and the accuracy of your neural network starts decreasing. So you can have to trade off, but it's miraculous, but it's a black box. Extreme gradient boosting, it's a tree-based approach, decision trees. If this variable is greater than that value, do something. If it's less, go do something different. You develop a bunch of these trees, decision trees. So there's one, there's one, there's one. Boosting the information from the first tree is carried into the second tree when it's formulated, which is carried into the third tree, which has the impact of focusing the fitting effort on the hardest ones to predict. Okay, so it's tree-based. It gives you the importance of the variables, not the statistical significance. So for us as scientists, to get a prediction, we don't really like that, me either. But the reality is we are trying to predict. This will at least give variable importance, but not significance. And the way it's basically working is in the first tree, the orange is sort of the line that goes through this. Second iteration, it gets a little bit better. It goes right through that. Third iteration, it gets better. And you finally get to a point down here where your trees give you, in a perfect world, a residual of 0. And that's the idea of it. And logistic regression, again, this is something that you'll all be familiar with. The basics of that is you use a sigmoid function to get a probability, put in your X values of your logistic regression model, and then you get a binary classification, happy or sad, or bathymetry or noise, or something like that. Its fitting is iterative, really, really time consuming to fit. And we'll be seeing some of that. So finally, to get to some of the results, how well are we fitting? Because what we're trying, at this point, all I'm trying to do is measure with this metadata that I have, how much signal is in there for predicting bathymetry. So if the R squared was 0 in all of these, then it's pointless to continue going on. So when we look at the R squared, and that's a pseudo R squared because we're dealing with a classification problem, so you have to use log likelihood and all this other kind of stuff instead of square error. You can see that realistically, the R squared in general, where you've got 1 million or anywhere from 1 million to 7 million points is working pretty well. Each of these represents one of the different tiles. This was the easy one. This is the hard one. This is the shallowest one. This is the deepest one. This 6.5% of the points are bathymetry, so that is kind of hard to predict. Here, 0.4% of the points are bathymetry, so that's really, really hard to predict. Yeah, that's the one you let the kids play with. It's 76.1. Do that with your eyes closed. This one about 21%, but that gives you a little bit of a sense of how difficult are the tiles. So as you look at this, the R-squared is reasonably good considering that there's anywhere from 1 to 7 million points represented. R-squareds are generally about 0.4. Global classification accuracy is really, really good. And even on the one that's really hard, it's very, very close to being 100% accurate. But we'll get to that. Okay. Now, before we do get to that, again, machine learning is about prediction. It's not about explanation. So in fact, generally in this stuff, you don't really care what variables are contributing to the prediction. But fundamentally being a scientist, I want to know. So these are the 4 tiles from shallowest at the top to the deepest at the bottom. And when you look at the variables that tend to be important in each of these, for each of these tiles, the things that start coming out is the topography that I have was never important. And there's no consistency. It's not as if always the return numbers are important. Now, topography, keep in mind, it doesn't mean that topography is not important. It just means that the way I extracted topography is not important. The variables that I use are not important. So don't take that as this paper is no good. No, it's more my measures are questionable. So if we look at how good the models are, again, before we do that, let's look at the time it takes to fit. So again, same thing. The shallowest tile is on the left, deepest tile is on the right, 7 million observations on both of the tiles on the left. And you can see that regularized logistic regression, that model took about 7 hours to fit. And so my thanks to the IT people, because I'm able to do this from home, let this thing run and hit the button and wake up Sunday morning. The results are miraculously waiting for me. But you can see that in general, the regularized logistic regression always takes a long, long time because it's iterative. So if we now look at the results, up top you have the false positive rate, which is really the percent of bathymetry that was correctly classified. So in this one, for example, in the hardest one, there were 4,000 points that were bathymetry. And basically what this means is about 40% of them were found. Okay, so we obviously want really, really high results, but it's in this tile, the easiest one, that in that case, 76% of the points we had were bathymetry, and about 95% of them were actually labeled bathymetry. Okay. Now this is false positive rate. So that's the percentage of the noise or the things that were not bathymetry that we labeled bathymetry. So we'd really like that to be relatively low. And you see for the hardest tile that we've got, it is relatively low. So again, it really seems like this tile that is the hardest is performing reasonably well, and that these are not performing so well. Well, in fact, I can classify all bathymetry correctly. I can label all bathymetry correctly, and it's really not all that difficult to do. Now, you'll see that it's meaningless, but this is what the confusion matrix for the difficult one looks like. And so when you look at that, you've got the concept of the user's and the producer's accuracy. So in the case of this tile, there's about 3,900 points that are truly bathymetry. And in the case of this, which happens to be for a neural network, got about 1,600 of them labeled correctly. So for me, the person who's doing the classification, who has produced the classification, there's 3,900 points. I labeled 1,600 of them correct. As the producer, I got 41% of them correct. But with my classification, I would hand to you, the users, 2,500 points, and I'd say there's 2,500 points that are bathymetry. because that's what my classification said these are. And your question should be, well, you've given me 2,500 points. How many of them are actually bathymetry? Well, about 64% of them are. So if I want to actually label all the bathymetry correctly, sorry, it's really, really easy to do. All I have to do is label all the points bathymetry. Okay? So I have now classified everything as bathymetry, and so now I say there's 3,900 points of bathymetry out there. How many did I correctly label as bathymetry? Well, 100% of them. Okay? But of course, I'm going to hand you 1,000,000 points. This is my classification. I'm going to hand you 1,000,000 points and say, there they are. They're all bathymetry. And you're going to say, yeah, but what percent are actually bathymetry? Well, 0.4%. So the things that I showed earlier are a bit misleading, and that goes to the idea of the trade-off between getting the true positive rate and the false positive rate correct. Some of you will have seen this. This is a receiver operating characteristic curve, and it shows the trade-off between the false positive rate, the true positive rate. So basically, when we produce a confusion matrix, we always say anything with a probability of 50% or greater will be labeled as bathymetry. This basically says, well, you can change that decision threshold, change it to something else, and what you can do is get a false positive rate of 10%, you get a true positive rate of 50%. So it goes to that trade-off that I showed. Now, the optimal point or unoptimal point is right there, the inflection point, and it turns out that inflection point is where the true positive rate and the true negative rate intersect. So in this case, if I change my decision threshold, instead of saying everything greater with a probability greater than 50% of being bathymetry, I say, well, I'm going to use a threshold of 0.32. In some ways, it's more optimal because it makes that trade-off. And what that does is it takes that confusion matrix, which is the same thing you've seen before, and it converts it into that. Now, that you may be looking at and saying, well, why is that useful? Well, the reason that's useful is because it has strengthened the bathymetry signal. Prior to doing that, what I was looking for was 30 over there. I'm looking for 3,900 bathymetric points out of 1,000,000. Now what I'm looking for is 3,800 bathymetric points out of about 25,000. So if I then take that, go back in and refit the model, I would love if I now refit the model, do this again, and the next time I do this, I come up with something like that. Because if the signal has strengthened to the point that I can do that, I now am at a point where I can say there's 3,800 bathymetric points out there, and I identified it. I got them all correct. Hand you 3,800 points and say there's 3,800 points, and all of them are correct. So this is kind of where I've gotten to and have just started. I'll give you a teaser on where I am. This is R squared. I've done 10 iterations like that. So what I've done is I did a classification, took that intersection of the true positive rate, the false positive rate, scraped off the points, refit the model, did it again, did it again, did it again, did it 10 times. And what we would ideally like is we'd like to see R squared going up. Because I've eliminated those points that were causing me problems, I'd now like to say I've now refit a model and R squared's going up. Not really happening. I would like my user's accuracy to be going up, and as I start doing this, that's doing it. But if I look at my producer's accuracy, and again, that's how many of those points that I find and get correct, it's going down. Okay, so needs work. The confusion matrix also has gone from what you see over there on the left to this over here, and this is clearly not acceptable to say I've now found 88 points that are bathymetric, and we know there's 3,900 out there. So I'm working on users and producers accuracy look great, but needs work. So yeah, don't always just go off users and producers. So one of the things, final thing I'll talk about, operationalizing this, if you followed what I've been doing, basically we have a NOAA classification And then I'm trying to measure the strength of signal of metadata. But what we're ultimately trying to do is improve the chirp algorithm. And so what we want to do is assign a probability to each one of those pulses. And so currently this paradigm kind of says, well, give me a classification and I'll give you a classification and I'll give you a probability. So it's quite circular. So the way this will work operationally is that chirp in its current form will do a classification and say, here are to our best estimate, here are the points that are bathymetry. Once that information is obtained, that can then go into extracting all of the metadata that I talked about. Once the metadata get extracted, the first machine learning model can be fit, and then that the confusion matrix can be thinned out to some yet to be defined convergence threshold to say we now have the essence of the data that we're fitting our models on, and we can apply that. Then we will send that information back over to chirp. Chirp will be rerun again, probabilities that we have at that point attached to each individual pulse, and then the cycle will start again until we get to some point where we have some sort of convergence on that. So the operational, right now, it's a matter of measuring the strength of the signal, but the ultimate goal is operationalizing that. The ultimate goal being not how strong is the signal, but did we in fact decrease the human effort required? Did we find the same number of bathymetric points or more bathymetric points? Basically, do we do as well as human beings? So with the final thing, just the next step, there's a few things that I have to do. One is I've only looked at a single resolution of a digital elevation model. Topography wasn't important. My measures of topography weren't important. Maybe it will be. Few other things. One is I'd like to get a universal model, not separate models for each tile, or a universal suite of variables. I'd like to do that. Or I'd like to do validation protocols, or that, or that, or that, or that, or maybe I'll do that, or I've also got to do that. There's a few more that you can't quite see. Okay, well, with that, I guess I will stop and just ask if there are any questions. Yeah, no, not the usual kind of talk, is it? Jordan.
Yeah, so you're using this for LiDAR, and a lot of the metadata you're collecting is kind of like how these attacks scatter you get from sonar. I'm not ocean mapping, but do you see where you're at right now, in fact, that you're starting with ocean mapping, do you see how you can apply this safety equipment to attack scatter with deep sea ocean mapping?
I don't know. I think that's where my learning curve about how all of this stuff is done is just, it's just too much in its infancy. And I know I've sat down with Giuseppe and talked about some of the things that he does and just kind of thought, okay, I see what's going on, but I just don't have the knowledge. I suspect that you can extract metadata from all sorts of stuff. So I suspect that there is additional metadata, but I also suspect that multi-beam analysis has been around for so long that that's pretty well established. And it'd be interesting to look at, but I don't know. And certainly my knowledge at this point is not sufficient for that. You're very brave. Other questions? Yeah, Tony.
Machine learning is notorious for, you say data hungry, so we use a lot of data. So it trains very well when you have data, but it often will fail where you step outside of that data set. So and you're looking at some few specific tiny sites. So how robust or how well do you think it should be outside of the different bottom types and using Shahar?
Yeah, there's so many things around that question that one of the things, for example.
I have time.
Yeah, okay, okay, good. Now, one of the things I looked at is within these data sets, I was getting really poor results. So I shuffled the data sets, and believe it or not, that made a big difference. And the reason for that is a lot of bathymetry was, if this is the whole data set, a lot of the bathymetry was in that block of code. So the way neural networks work, for example, is it sends down batches of data. So it was grabbing a batch of data that had no bathymetry and saying, okay, now I've got to fit a model on bathymetry or not bathymetry. I don't have any bathymetry. So you've got that kind of thing that causes problems. The other thing is, it is really, really specific to one particular tile. So one of the things that I did, that I've just toyed with, is I took all those tiles, threw them together, fit a model on them, and said, okay, now how does it work? How well did it fit each of the individual tiles? So threw all the data together, fit a model, did the prediction, and broke them back up. No, just absolutely got hammered. So that's where I said one of the things to look at is a universal suite of variables. So I said, okay, well, if I know that this set of variables is always important, at least I can say when I go to fit a new model, I can just take that suite of variables and throw that in there. I don't have to worry about any of this stuff, because a lot of the metadata I'm extracting, it takes, not only do the models take a long time to run, but just extracting metadata takes hours and hours and hours and hours. So I can't even get a universal suite of variables that are fitting the whole thing. So applicability across a lot of things, I really have my doubts about it. The thing that's encouraging is with the validation that I've done, when I fit a model for a single tile and then validate on that tile, I get strong validation, which at least says to me, I can keep using it for this tile. But to take a model from this tile is valid. And it doesn't matter whether it's extreme gradient boosting or logistic regression. Anything else next Friday afternoon? All right. Thanks for being here.